Hello, honors physics students. Let's start by going over some homework. So have your Cutnell-Johnson and your textbook in front of you and all the problems you did. So let's start with the focus on concepts here in Cutnell-Johnson. Rays of light coming from the sun, mirror parallels of reflective concave mirror. It's basically just a review of what we had done in the original note I gave you. We had this diagram. Looks like this, right? So we have our concave mirror. We know it's concave, the light's coming this way, sort of caving in around it. Also, it's called a converging mirror. Converge means to bring light together. Of course, the light rays converge, they meet at a single point, that's the focal point. So yes, we're talking about letter D here. We'll cross at the focal point. So pretty simple, nothing fancy here. All right, let's start to take a look at some of our ray diagrams. And so let's start here in number 14. Here we go. All right, so this is number 14 in Cutnell-Johnson, and you were told is a concave mirror. So here's concave, and again, the light is coming this way, so it sort of caves in around. You don't have to identify the type of device, but it's always a good idea to think about it so you're linking this two together. A concave mirror is a converging mirror, and that's why the focal point is on side, it's always on the concave side. And so here's our parallel ray coming here, reflecting through the focal point. I did the central ray. Remember, our trick here is to imagine flipping this over, so you measure the height of this on the ray diagram, you exact same distance below, put a single dot, you connect the dots. This guarantees our angles to be the same. We see that these light rays are diverging, they're spreading apart from each other, which means they're not going to make an image over here. So what do we do? Well, remember, if we're standing over here, when it comes to light, humans are stupid, so you think light comes from back here, so you just trace the reflected rays backwards. Be very careful you're tracing the reflected rays backwards, not the original rays, because they haven't interacted with the device yet. We're using a dashed line to show those reflected, those imaginary reflected rays. We're showing a dashed line because it's imaginary, and also there's no arrows on here. All these details really do matter. Make sure you are putting arrows in every single one of these rays, though, because this is how it's done. All right, and then so wherever they connect, that's where the image appears to be. And so here it is. Always a good idea to label it, draw it somehow different. But the ray diagram is not complete unless you've drawn the image. So these are all the details I'd be looking for. Arrows on all of your rays, dashed lines, and we trace the rays backwards, no arrows on those rays, and definitely drawn the image from the principal axis to the connection point. Let's compare this to the math, and I assume you did the math first. Even the problem, even if you didn't have to, that's always what you're supposed to do. This is my advice I gave you in the last video. Always do the math first, right? And so we expect it to be 28 centimeters behind the mirror and 7.6 centimeters in height. So the focal length here is 18 centimeters, and all these tick marks are evenly spaced. Here's 18 behind, here's 36 behind. This looks like it's about 28. Yeah, it kind of does, right? That's why we always do the math first, because we know we're going to get the math correct. It's also a good idea to describe your image, even if the problem doesn't tell you to. This is upright, put in the exact same way as the original object. It's clearly magnified, and it is a virtual image. Now, let's remind ourselves, why is it virtual? Well, virtual means that it can't be projected onto a screen. So if this is a source of light, like a lamp or a candle, I put a screen here behind the mirror, there's no way to project the image onto the screen because the mirror literally is blocking the way. Light does not go through mirrors. Think about that for a second, right? Light does not go through mirrors. That's why we're using these dashed lines, where we think the light comes from back there. Light's not really going through the mirror back there. We just think light's coming from there, so that's how we see the image. That makes it a virtual image. Also recall that virtual and upright always go together for a single device. We also said that a virtual image is when you have to trace light rays backwards, which is exactly what I have to do here. So even if the problem doesn't tell you to, it's always a good idea to put down all the categories of image descriptions there as good practice. Let's take a look at problem 15. Here is a convex mirror. They told you it's convex, so it's drawn the other way. Light's coming this way. The concave side's on the other side. That's why the focal point is labeled on the concave side, as is the radius of curvature. We do not label F and R there. That would be completely wrong to do that. If you have done that, you've got to get rid of it. Mirrors only have the one focal point. It's always on the concave side. While these tick marks are evenly spaced, this is 50, this is 50, this is not the focal point. So if you had done that, that'd be very confusing. You've got to get rid of that. This is a diverging device. You always want to think about convex and diverging go together for mirrors. And so the parallel ray diverges, not just at any angle, it diverges as if it came from the focal point. So you sort of trace it backwards there. If you had drawn the parallel ray going through here, well then you're very confused. And this is what I'm talking about, that this is not the focal point. And if you've done any of those mistakes, you definitely should pause the video and try it again on your own. Now hopefully you did the math first, and you should have noticed that when you did the math and you did a ray diagram, if you've done it wrong, they don't correlate at all, but that's how we do the math first, right? So here's the parallel ray diverging. For the central ray, again, you just flip this over, put the single dot there, get the equal angles. You see these rays are diverging, which of course makes sense because it's a diverging mirror. You trace them backwards, and here's where they connect, and that's where you draw the image. Remember, the ray diagram is not complete unless you've drawn the actual image. Now, some students get a little confused and say, well, I know for a diverging mirror I'm going to have to trace light rays backwards, and so they show this ray, they show the trace back ray, and they don't show the reflected ray. Now, that's also wrong. If that's something you did, fix it now. We draw the incident ray and the reflected ray every single time. Incident ray, reflected ray. And then if you have to trace it backwards, you do that also. But if you're not drawing the reflected ray, that's incorrect. Alright, now if you want to do the focal ray, this is where it's a little bit more of a challenge. This is where you take a light ray from the tip of the object, you aim towards the focal point on the other side. It reflects back parallel, and then we trace it backwards. It should meet the others. Here's the math answer, 16.7 centimeters behind the mirror. Now, if you got different answers here, hopefully you recognize what you did wrong, and you should have realized that this is a diverging mirror. They didn't tell you it's diverging, but it says convex, and they go together. And if you go back to the notes, we know that diverging devices have a negative focal length. Now, the problem won't always tell that to you. They'll just say what the focal length is, what the radius of curvature is, but it's your job to put this in as a negative 50 centimeters. If you didn't do that, definitely pause the video and try it again. You should be able to get the correct answers when you do so. So that's up to you to remember that converging devices have positive focal lengths, diverging devices have negative focal lengths. Let's check our numbers here. It says 16.7, the focal length is 50. Does it look like it's about 16.7, about a third of the way? Yeah, it kind of does. Right? And that's why my advice is always do the math first. This way you know where to expect the image to appear and what it's going to look like. You can actually measure things to scale and actually literally draw the image without doing the ray diagram, and then sort of make the ray diagram happen around it, which is not the best way of doing it, but in a pinch you could do that. Some students maybe aren't as good at doing ray diagrams, but they're going to get the math right, so maybe you want to try that. Let's take a look at number 16. Oh, sorry, of course we also want to describe it. It is upright, put it the same way, it is clearly reduced, and it is a virtual image. Once again, the image appears behind the mirror, but also, hopefully you remembered, as I mentioned last time, diverging devices only do one thing. They only produce upright, reduced, and virtual images anyway, which means if the problem asks you to describe the image and it tells you it's a diverging mirror, you don't even have to do the math, you don't even have to do the ray diagram, you know it's going to be upright, reduced, and virtual. The only possible exception is if the object is directly up against the mirror, in which case it's still virtual and it's still upright, but we kind of don't say it's reduced, we kind of say it's life size. It's right up against the mirror. There's really no change in the size of the image. But for everything else, it's always going to be reduced. Now let's take a look at number 16. Okay, so again, we have a convex, a diverging mirror. We do our rays, just the same ones I did before. You trace it backwards. Here we find the image. There's nothing fancy here. If you want to do the focal ray, again, that's where you start from the tip of the arrow. You aim towards the focal point on the other side. We stop in the mirror. We reflect by parallel, trace it backwards. It meets all together. If you had done the math, you should be getting negative 5.77. This is 7.5. That's what it looks like, about negative 5.77. And everything correlates, right? Our math correlates with the ray diagram. Things are looking good. Then you were asked to move the object closer in. Here's our parallel ray again. Here's our central ray. And here's our new image. And again, if you've done the math, negative 3 centimeters. Yep, looks like just shy of halfway. Things are looking good. But this problem is really about comparing. And you see when you move it in closer, the image distance became smaller. Remember, image distance is measured from the mirror. Here's the original image distance. Here's the new image distance. That is a smaller value. HI clearly became larger. This new image got larger as you move the object in closer. And that's what I was saying before. The closer and closer you move the object in, the closer it's going to be life size. But no matter what, it's always going to be upright, reduced, and virtual, which again always goes along with diverging devices, no question at all. At any point during any of this, if you're getting any of this wrong, please pause the video, go back and try it again, try the ray diagram, do the math. You shouldn't just be writing down what I'm writing down. This is very much something you have to do on your own. You have to work and work until you get these ray diagrams correct. Let's go on to problem 36. Here's a concave mirror. Light's coming in here. We said the idea is it's sort of caving it around. Is that converging or diverging? That's converging. So here's our parallel ray converging to the focal point. Here I did the focal ray reflecting back parallel. You could have done the central ray. I decided not to. You know what? For this one, I said I don't want to do the central ray because sometimes the focal ray is easier. Because with the central ray, you have to do the whole measuring and putting the dot and lining things up. And some students say, you know what? Focal ray seems to be easier, and that's okay. For any of these, you don't really need 3 rays. 2 is sufficient as long as you get 2 rays to reflect and intersect. You've located it. Make sure you draw on the image. Make sure you have arrows in all your rays. All those are the things I look for. All those details. The math shows 7.5 centimeters in front of the mirror. Here's 5. Here's 10. We should get our image to appear right there in between. That makes sense. And an image height of 1 centimeter. Things are looking good. Again, it's a good idea for you to describe the image. And here it should be inverted, reduced, and real. It's clearly been inverted. It's pointing up. It's pointing down. It's clearly been reduced. And it's a real image. Now, why is it real? Well, a bunch of different ways you could say it. One, we never had to trace any light rays backwards. That's good. A second one is it's inverted. Inverted and real always go together for a single optical device. But really, the strongest way is imagine a screen here. If this is a source of light, I put a screen here, can I get these light rays onto that screen? You bet I can. These light rays do reflect off the mirror, and they actually meet at this location, so a screen there would actually show an image of that object. That makes it a real image.